Formation of buffers. This is a PowerPoint that I am using from the AACT website. So in this, they gave examples of different scenarios: buffer form using a weak acid and a salt containing conjugate base. And just as we've done before, they drew out what it looks like inside of the beakers. And that way you can see what it looks like. Then I showed you example number 1. I made a point to point out this equation here. This is your Henderson-Hasselbalch equation. And we also talked about how to get your pKa for when it's not given to you in the problem. And it's a simple process of taking the Ka, which we have to provide you in the problem, or you have to have a table which you can look it up. You plug that in, that gives you the pH based on that pK, on the Ka. And now I plug that in here. This is the pH that I desire. And then I have plus log A minus over whatever molarity I have desired. Okay. Recall that we can write acid bases in a generic form, and that's what the A minus and the HA is referring to. The H is going to be the water, which is not a factor in our equation. Okay, once we have that, we're going to use our algebra to solve for A minus. And once we have that, if we're looking for the mass of the A, because we're going to actually physically measure out the mass, we just need to convert it from its molarity, which is moles over liters, to liters that we are desiring, which in this prompt was 25. And then we need to make sure we have our molar mass for this conjugate that we're working with to get how much we need. And then we have a buffer formed using a weak acid and a strong base during partial neutralization. A buffer can be formed by neutralization because conjugate base is produced when the neutralization reaction occurs via the reaction below. So again, showed you an example of that. This is example number 2. The key thing on this is that the volumes are additive, so working with moles as opposed to molarity will provide the simplicity. You'll see that on your activity. Very similar setup. The only change is this step right here. So everything follows the same as what I just previously did. It's just now I'm actually going to put in what I got. And I'm going to solve using algebra. Okay. And once I have my moles for the A, then I need to convert those over to liters and then milliliters. This also showed that the buffer can be formed using a weak base and a salt containing its conjugate acid. Just giving you the different ways that we can form a base buffer. And so we have another setup here. Calculate the mass in grams, which will CI to 535 milliliters at 0.15 molar CH3NH gives you the KB. So the previous 2 problems we worked with Ka. And I want to produce a pH of 11.10, changed by addition of the solids negligible. So again, I'm using the Henderson-Hasselbalch equation. This time I'm using it with bases. Ka can be found by using the Kb. All right. So this is only your change right here. This is what gets me to the Ka, that relationship with the Kw. Once we have that, we're back to normal. We find what our pKa is. We're going to substitute it in and use our algebra and then convert it over to get our mass. Buffer formed using a weak base and a strong acid during partial neutralization. So another scenario in which a buffer can be formed. Again, I'm given the KB. So again, here I have my relationship there. Volumes are additive, just like we saw with the example number 2. So I have to work with the moles. Again, my Ka can be found by taking the Kb with the Kw relationship. I sub in my pKa. And again, I'm going to get down using my algebra. And then I want to go in here and I'm going to convert over. All right, let's get to your activity. So I went through this with y'all, and one of the first things I pointed out was this problem does not give you what the pKa is. So this is your first step, is you've got to get your pKa. And so, where is it? Usually it's going to be given to you, okay? So like here, I give it to you on this table for your activity. So this one here, it's given to you right there. We solve for the pKa. I'm going to sub it into my Henderson-Hasselbalch, and then I'm going to use my algebra. Now the only catch is, it's usually this step right here, because you have this log. So what you need to do is do the second log of that number, and you will end up back to your algebra and able to produce what you need. Then once I have that, I come over here and I'm going to convert. And since NaNO3 weighs 69, I put that on top and I will have my grams. So pre-lab questions, I'm going to go through this real quick because I want to get to the math part of it. This gives you a scenario. You can read it for yourself. And then I gave you a separate scenario as well. In this case, the pH was equal to pKa. And you can read what I have written here. And then it gives you a second scenario in which buffer B has twice the number of moles, and it asks you to justify what will happen. And so the key is the fact that it is twice the number of moles compared to A. Again, we're back to the twice the moles. Well, what happens? Is it going to be more resistant to change? Absolutely, because I have twice the moles in there, or I have twice the little warriors in there that are going to keep it from changing too fast. So think of those little molecules as being like little warriors, and they're resisting the change. Okay, so then we got into what our main point is, and this is why I like this activity, because I can give you each a different pH that I want you to get to. You actually get to do the calculations, and then you go back into the lab, you go measure out your stuff, and bam, you've got it. Okay, so I go ahead and I give you what your sodium acetate is, your Ka, and then each table gets their pH. So then you do your calculations just like we did over here. Except now you've got to make sure that you do this step here because it's not given to you. Okay? And so over the first part, you're getting your grams. So you follow along here, you put in your numbers, and you'll produce a good value. Okay? Check your answers at the end before you begin to make sure that you have calculated correctly. Okay? Then, number 4 asks you to determine the mass of sodium acetate. Okay? So, and it should say the moles, sorry. But you're using your Henderson-Hasselbalch equation. The key thing, like we saw in the other ones, number 2 and number 4, is that we got to convert moles because they're additive volumes. Necessitate no longer using molarities. So that's the only change here. One of the first things up is I do need to convert liters to moles using idea of molarity. Once I have that, I've got my pKa, I've got my desired pH, and I want to solve for A minus. Then the change is right here. Since I'm no longer solving for grams, I'm going to now be taking this number that I got here and I'm putting it here. Now I want 50 milliliters, so I'm going to put it here. And I'm going to use my algebra. And this is all the algebra that guides you through to make sure that you are thinking through the process of how to get those isolated. Once you have that, my last step is just right here. My moles of A equals my mole of OH because it's a 1-to-1. So when I have 0.030 moles of OH, that's how many moles of A I have. So then I just need to convert that over to the moles of sodium hydroxide and then convert that over to liters. So then you perform your calculations with the pH that you're given and then check your activity. So again, this is my table for you to check, and on that last one, this is a column you're looking at. So it doesn't give you the milliliters, but it gives you the moles, and you just need to check your number to make sure that you are matching mine. Then you'll do your activity, and then I need you to do your analysis. So we need to do percent error, and since this lab is really pretty good about getting us a pretty reasonable number, hopefully your percent errors are down low. This reminds you how to do your calculation. Make sure you complete them with your pH values. Then these are just some follow-up questions. Like this one says, well, why can't this lab group do a buffer with hydrochloric acid and sodium chloride, and explain why that procedure won't work, and justify your answer using net ionic equations. So I don't have that included here, but you are to do that. Key thing to remember is that a buffer is composed of a weak acid and its conjugate base. That way we have both acidic and basic components present in the solution resisting change. And HCl we know is a strong acid, so it doesn't fit into that. Everything's going to dissociate, and so there's nothing undissociated in there to keep it from swinging. Then question 3 asks you to circle the beaker that best represents the particular diagram for buffer 1. Think about some things. So answers vary depending on what your assigned pH compared to the pKa of acetic acid will be. If your pH is lower than the pKa, then the middle beaker is yours. Okay. If you have a pH higher than the pKa, then yours is represented by the left beaker. And then if your pH equals the pKa, you're the right beaker. And notice you're looking at the molecules and seeing which one is superior than the other. And notice this is when they're equal, and that's why the pH equals pKa. It's observed that the buffer 2 changes more significantly than buffer 1 upon the addition of a strong acid. Explain. So this goes back to that idea that if I have more molarity in there, then they're going to go in there and resist change more so than the ones that have less in there. So anyway, this is your activity, which leads us on to your dual credit AP number 16, in which you guys will be doing these calculations and making your own buffer solutions. So I hope you found this informative, and live long and prosper.